Okay, so we're going to go through the Unit 6 practice test, okay? This is our review for the test this week. And you are going to need out a way to calculate some of these numbers by either by hand, which is cool, but I would highly recommend a calculator like the ones I post on your to-do list. Okay, so the two ones I recommend having out is this one. We're given a mean, sample size, standard deviation. You can calculate the confidence interval. Okay. Also, on this one, it says, similar two sample t-test, one sample t-test. That's kind of what you're going to need also. So let's go through this first question. It says vacation days. The distribution of the number of vacation days per year offered by different U.S. companies is below. We collect data on the number of vacation days from a random sample of 60 companies across the United States. Why is it okay to use these data for inference even though the population is small? Okay, for a question like this, you got 60 companies across the U.S. Obviously, there's a lot of companies in the United States, and so a sample of 60 sounds kind of small. But with the tools we have now, we'll use the student t-scores instead of the regular normal model. And so you're going to state that by saying something along the lines of, it is large enough to use student t-scores. You can really only you can use student t-scores with like a small sample, like 2, 3, or 4. Ideally, though, you want as much as you can get, but it's large enough to use student t-scores. Okay. Large enough to use student t-scores. The mean and standard deviation of the 60 companies in our sample were 22 days and 9 days. So what they found was an average of 22 days and a standard deviation of 9, respectively. Specify the sampling model, shape, center, and spread for the mean number of vacation days of such samples. So the shape, that's going to be like a t-score. The center, that would be like your average, and the spread, that's going to be your standard deviation divided by the square root of your sample size. Okay, so expect on the test, just have to identify those 3 things independently. Okay, so we can say the shape, that is going to be t. Now we will also want to put the degrees of freedom with that, which for this case, for one thing, it's just going to be sample size -1, n -1. I probably should put that on there as well. It says 60 companies. That'll be my 60. So let me back up a moment, okay? Given this information, they gave us the average, they gave us the standard deviation, and they gave us the sample size, okay, from the sample. Our shape is going to be based on our student's t, which is you have to have your degrees of freedom to know which student's t values to use. Remember, it changes based on the sample size, okay, or on the degrees of freedom. So degrees of freedom n -1, we're going to put 60. Let's just go ahead and say df is going to be 59. So t 59, that would be the shape. Okay, it's not a normal model. It's going to be t 59, student's t. All right, center. The center is going to be our average. Okay, that would be 22. But our spread, oops, our spread, that is the standard deviation divided by the square root of our sample size. I'm just going to leave it like this. 60. Oh, I like square root of 60. I'm being so silly. Okay, but our spread would be the standard deviation of 9 divided by the square root of our sample size. That is going to be your spread value. Okay, that is that's like our standard error. So that right there is our standard error of our average. Okay, so we find the average. That's the standard error of that. Find a 95% confidence interval for the mean number of vacation days offered by U.S. companies and interpret the results. Okay, so we need a calculator for that. 95% confidence interval. That is the equation right there. So sample mean is 22. Sample size is 60. Standard deviation they gave us was 9. Okay. Hit calculate. And it gives us these numbers here. So let's interpret that. Okay, you can be 95% confident that the population mean mu falls between 19.68 and 24.32. So that right there, that's your whole entire answer. Okay, find a 95% confidence interval. So we can say our confidence interval would be, and it says 19.68, comma 24.32. I'm going to put parentheses around that. So even though the sample said the average was 22 days across US companies, that was the average on the sample. So with these calculations, what we just did was, if we're 95% confident that if we got data from all the US companies, it's probably not going to be 22, but we're 95% confident that the actual average of all companies is between 19.5 and about 24.5. Okay, so we would expect the actual average to be between those numbers. We realize the actual average might not be 22, but it's going to be probably close to it, and it's going to be probably between those numbers. Okay, we're 95% confident. So it says interpret the result. We can literally copy what it says, you know, pretty much word for word like that. Okay, so we can say, oops. Okay, so we are 95% confident that the actual mean vacation days offered by US companies each year is between 19.68 and 24.32 days. Okay, there's a few different ways you could say that, but that's pretty much the gist of how it should be phrased, right? When it says interpret, it means take those numbers and make some meaning of it. Okay, by meaning, I mean like just put it into context. What's the question about? Just regurgitate that with the numbers placed in there, almost like a Mad Libs type style, right? So 95% confident the actual mean vacation days offered by US companies each year is between 19.68 and 24.32 days. Okay, that's the actual average. Are we 100%? No. Okay, we could have gotten a weird sample that was too high or too low. Goldilocks, right? We don't know, but we're based on the stats that we computed. Okay, that's the best we got right now. Okay, it's between there. All right, so please stop me if you guys have any questions. If not, we're going to move on to the next one. All right. A father is concerned that his teenage son is watching too much television each day. Since his son watches an average of 2 hours per day, that's probably going to be important. Okay. His son says that his TV habits are no different than those of his friends. Since his father has taken a stats class, he knows that he can actually test to see whether or not his son is watching more TV than his friends. So that might be important. Okay. The idea that more sounds like greater than. Okay. The father collects a random sample of television watching times from boys at his son's high school and gets the following data. So it might be kind of difficult to see because they're all kind of jammed together, but each one of those writes 1.9 hours. One boy said he watches on average per day 2.3, 2.2, 1.9, 1.6. Okay. So is the father right? That is there evidence that other boys average less than 2 hours of television per day? Conduct a hypothesis test, making sure to state your conclusions in the context of the problem. Okay. So where I originally thought it might have been a more than, a greater than problem, we're actually going to test if it's less than. Okay. So this is kind of saying whether or not his son watches more TV than his peers. So if he's watching 2 hours, his dad thinks that his friends, or at least the boys at his school, will watch less than 2 hours. So we're trying to test to see if his peers watch less than 2 hours of TV, or if they watch 2 or more. What if they actually watch more TV than what he does? Okay. So conduct a hypothesis test, making sure to take your conclusions in the context of the problem. So we need to start by identifying our hypotheses. Okay, null hypothesis and alternative hypothesis. So the hypothesis is that the average is going to be 2 hours. Okay, that all students, at the school, all boys at the school watch TV for 2 hours. That's what we're kind of assuming. Okay. The alternative, what the data is trying to test for, is that the boys actually watch less than 2 hours of TV. Okay. So conducting a hypothesis. So is the father right? That is there evidence that the other boys averaged less than 2 hours of television per day? Okay, so that's the indicator of what your alternative hypothesis should be. Okay. Remember, the null hypothesis is always if nothing changed, if everyone's the same, it's all like vanilla. Okay. All right. So now we can identify a few things. We have these data points, so we got to find like their average, the standard deviation, the sample size, degrees of freedom. Okay, so we should identify all of that kind of stuff. Sample size, freedom, and then we also should probably find our standard error of our mean. Okay, that's going to be our standard deviation divided by the sample size. And yeah, that's going to give us like a t based on our degrees of freedom, and then that will then give us a p-value where our t should be less than something. Okay, whatever we get here and all that kind of good shit. Okay, sorry, give me a second. I will. So given all those data points, we got to find the average, the standard deviation, the sample size, the degrees of freedom, our standard error of our mean, our t-score, and then a probability of getting that t-score. So we need to use this website to do the one sample t-test, right? We have one sample. Sample one, let's type this stuff in. Let's see, 1.9, 2.3, 2.2, 1.9, 1.6, 2.6, 1.4, 2, 2, and 2.2. Oh, the test mean. Here it says test mean. We're going to test that against 2. So we're not doing 0. That's usually when you're like trying to see if there's a difference. Okay, or there's no difference between stuff. That's usually where the test mean is 0. This time we're trying to test to see if that is less than 2. Okay, or 2. So that's we gotta make sure those match up. Because a lot of times you'll hear those have to agree. Your test mean and this value here have to be the same. Okay. Hit submit, and it's going to change this number slightly, but let's go ahead. Let's take a look at what we were given for our values here. So that's always going to reset to 0. Don't worry about that changing, but we used 2 and calculated it. So these numbers are based on the number 2. You can see right there and verify that it's 2. Watch, if I calculate it with 0, that's going to change to 0. If I use 2, it's going to change that number. The sample data is not equal to 0. We'll be looking down here where the sample data is less than 0, but it should say less than 2 when we recalculate it with the 2 there. Yeah, sample data is less than 2, p-value of blank. So that's the information we're going to need here in a moment. Okay, the average is 2.01. Our standard deviation is 0.3446. Our sample size was 10. Degrees of freedom then would be 10 minus 1, which is 9. That's even listed right there where it says DF. Okay. Our t-value is 0.0918. Oh, shoot, that's 0. There's an extra 0 in there. So remember, numbers close to 0 for t-values and your t-value, like your t-score, your z-score, those numbers that are close to 0 are close to the average. And so it kind of makes sense, right? If we think the average is 2, we calculated those numbers and the average was pretty much 2. And so our t-score should be close to 0, because this and this, what we thought it was going to be 2 was what we got when we calculated it. So a z-score or a t-score of 0 means it's pretty much on average. These t-scores and z-scores, if they're big, like numbers like 2, 3, 4, 5 that are far from 0, or at least further to 0 than 1, or 0.01, those bigger numbers mean they're further away from 0. Okay, it means it means you're gonna need a lower probability of that happening. So having a t-score of 0.0918 just makes sense, because it's pretty much right on average. So probability of getting, so if this was true, if all the boys watch TV for on average of 2 hours a day, and if we got results like that, that should happen about 53% of the time, roughly. That's the prediction from the stats. P-value less than 2. Okay, we're looking at this number here. We're going to ignore those top 2 numbers. Okay, that's for other scenarios. 0.5, 3, 5, 6. Okay, what that looks like is if you have a this is like your student's T of degrees of freedom of 9. Okay. Yeah, of 9 with an I guess I should be doing, that's fine. Yeah, let's do that. So at 0.0918, that would be like right here, basically on 0, and it's less than, so it would be shaded like that. How much of this is shaded? It's a little bit roughly greater than half of this drawing. So if I put it right on 0, that would be 50% of it will be shaded in. This is 0.5356. So it's a little bit bigger than like 53%, right? So it's a little bit bigger, and that shows us that, okay, those results should happen about that much of the time, they say. Okay. So conduct a hypothesis test. Make sure to state your conclusions in the context of the problem. So doing the hypothesis test, that's that. Okay, that is the test. The test is to get our p-value. Okay, that is the test. So based on this, we have to then state a conclusion. Remember, there's only 2 conclusions. Okay, there's 2 conclusions. So if our p-value, right, is less than 0.05, that number can change, but for this class, we've always used this number. We're going to keep it standard like that. But then just be aware, if you guys go to a college class or other class, they might change that number from 0.05 to 0.01 or 0.001 or something similar like that. Okay, then you reject, okay, the null hypothesis. If it is equal to or greater than 0.05, it's called fail to reject the null hypothesis. Okay, so because it's number like 0.53, think about it. This says if you got 5 cents or more, you fail to reject. That's 53 cents. That's the way I look at these decimals, right? If it's less than 5 cents, like 0.04, 0.03, you reject the null hypothesis. You say, that's not true. That's most likely true. If it's 0.05 or greater, like 5 cents or greater, then you say, well, we don't have evidence. It might not be true. Like it might be the case where we have to cancel out the null hypothesis. We just don't know. We just simply don't have the evidence to reject it. So you leave them both on the table, basically. It can be true or not true. We don't really know yet. Okay. So we would say a standard error of our mean. That's the observed difference. So if we need that number, though, the standard error of the mean, that would be the standard deviation divided by square root of the sample size. So if I was going to do that, I could calculate that on a calculator. I could say, so I can get that answer. Oh wait, standard deviation, that would be the 0.03. Sorry about that little writing there. So 0.3446 divided by the square root of 10 in a calculator. Oh, wait. Okay, hit enter. So when I calculate this number, I get a standard error of the mean to be 0.10897. Let's just use that number there. Okay, so why would you want this number? You'd want this number if you were going to calculate like the if you were going to, well, yeah, if you were calculating the stuff by hand, or you were calculating like a confidence interval, okay, you should use, you'll need that number. Okay, so just be kind of aware of how to get that number, right? Standard error of the mean. All right, so let's make a conclusion. Once again, because this number is greater than 0.05, we are going to fail to reject the null hypothesis. Okay. We can say the father does not have evidence that his son's friends watch less than 2 hours each day. Actually, I'm going to change, well, yeah, we'll keep that. All right, so let's see how I worded this. I said, we fail to reject the null hypothesis. The father does not have evidence that his son's friends watch less than 2 hours of television each day. Okay, so once again, we calculated these numbers by plugging that into the calculator. Observe the p-value for when the average, we're comparing this average against an average of 2. What we got for a p-value was 0.5356, so way above the value of 0.05, right? Less than 0.05, we would reject the null hypothesis. Since this is above it, and it's way above it, okay, we're just going to fail to reject the null hypothesis. He just simply does not have evidence that this is true. So far, it's looking like that's actually true, but we just don't have the evidence for either one. We're going to say we fail to reject this. Okay. Just don't simply have evidence yet. Okay. All right, leave that for a moment. And remember, I will be posting this online, this video online later today. Okay. So any big questions right now before we move to the last question? All right. Last question is all about how to read a printout like this and understand what it's asking. Let's read that question. A private high school is contemplating scheduling writing classes by gender. To assist in this decision, data of recent writing scores are collected and analyzed. It is believed that measurements of writing scores are normally distributed. Write a complete conclusion about writing scores based on the statistical software printout shown below. Okay, this is what was printed out. 2 sample T for male versus female. The male sample size of 91, average of 50.1, standard deviation about 10.3, standard error of the mean 1.08. Female sample size 109, the mean was 54.9, about 55. standard deviation of about 1, standard error of the mean about 0.779. The 95% confidence interval, okay, if we took the average male score versus the average female score, it looks to be a -7.5 to about -2.25. Okay, though that kind of means that it's skewed towards the female side of the scores. Okay, which look, I mean, if you think about it for a moment, the females on average scored higher. Okay, the standard deviation was less, means it's less spread of data, and their scores are generally higher. Okay, according to this data, the boys' scores were generally lower, but they had more of a spread to them. Okay, so it says here, based on this data, that the females scored on average, or that the average true difference is between 7.5 and 2.25, leaning towards the female scores. Okay, the interval is negative. Okay, for both cases, meaning it's going to lean towards the right side because we're subtracting. Average male minus average female, our results are negative. Okay, negative meaning the second number here is a bigger number. Okay, the average is bigger than that average. Okay, even when we account for all the other variables and stuff and the standard deviations, right? Standard errors, you kind of like make some adjustments. It's still going to kind of be a higher average towards the girls, it looks like. Our t-test, compare if they're the same or if they're not the same. It's a large value, okay? -3.6 is a large value, right? It's not close to 0. Anything above 2 or 3 is considered a large value. Our p-value is 0.0003. It's a small p-value. Remember that thing about 5 cents, 0.05. If it's less than 0.05, you have evidence to reject the null hypothesis. Okay, 0.05. This is 0.0003. And our degrees of freedom is 169.707. So remember, when you have a two-sample t-test, you are no longer just taking your sample size -1. There's a big calculation to get there, and the calculator is the best way to go for right now. Okay, this book recommends don't even calculate it by hand. So our degrees of freedom is some sort of thing that looks something weird, and it's not just n-1 anymore. Okay, it's a different way to get that. So, write a complete conclusion about writing scores based on the statistical software printout shown below. You don't got to do any calculations. It's just look at this. And as I was talking out loud, what I was saying was kind of like collecting that information. How do we write that, what I was talking about, into like a paragraph? Okay. So what we should do is let's start by talking about the p-value. Okay. So we're going to go ahead and there's a few ways you could say this, but basically we're going to, based on this p-value, okay, and this right here, this is like our null hypothesis, okay, because it has the equal. And this is our alternative hypothesis because it has the not equal to, okay. And because of that, okay, because our small p-value, we can reject the null hypothesis, okay, and we can say there's strong evidence that this is what's true, that's what's actually happening, that the scores are not the same, okay? So there is, we can say, strong evidence. Our p-value is 0.0003. And there is strong evidence, okay, p-value of 0.0003, that the writing scores for males and females are different. We're 95% confident, okay, so now we're going to do this confidence interval, okay. We're going to say that we're 95% confident the mean difference in scores between males and females is from -7.499 and -2.241, okay. This data provides evidence that the females will score higher, okay? All right, so we can say We are 95% confident that the mean difference in scores between males and females is from this to that, okay? From negative 7.499 to a negative 2.241, period, okay? We are 95% confident that the mean difference in scores between males and females is from negative 7.499 to negative 2.241, which might not have much context when you're just saying, hey, the mean difference is negative this to negative that. It's like, all right, can you explain what that means, the negative this, negative that, okay? And here's like the best way that I think to explain that. You can simply say something like, the data provides evidence that females score higher. Okay, we don't know how much higher. It might be by about 2 points. It might be by about 7.5 points. But according to this, we're 95% confident that the actual difference is in between those two numbers. Okay, at no point in our confidence interval do the males have a higher score on average. Okay, according to this, it says the girls will pretty much always, on average, not every person, but on average, score higher by a few points, okay, according to these numbers. Okay, is there a chance that it's wrong? Yeah, okay, a small chance. That's where the whole alpha, beta, and power levels come in, okay, and all the error chances, okay, type 1, type 2 errors. So I will go ahead and stop recording, okay, and we can answer any questions.